we've seen these problematic examples of limits that made us think that really we need to come up with ways of calculating limits rather than just guessing them based on a graph. Fortunately, there are some limits that are so obvious that there's really no calculation to do. Let's look at a couple examples. So for one example, let's find the limit as x goes to 4 of 10. Well, 10 it's a constant function. I mean, technically it's a function, but the value of the constant 10 function is just always 10. So what this limit is asking is, as x goes to 4, what happens to 10? Well, 10 is always 10. 10 doesn't care what happens to x. And so when x goes to 4, 10 is still 10. So this is 10, right? So the limit of a constant, it's just the value of that constant. There's not any calculation that we need to do. And furthermore, this isn't an approximation. This must be exact, right? Because this constant 10 function, it always produces 10. So what happens close to x equals 4? 10 is 10. All right, so limits of constants are no problem. All right, what about this one? The limit as x goes to minus 5 of x. Well, if you read this out loud, the value of this limit is obvious. So what we're asking is, when x goes to minus 5, what does x go to? Well, we just said x is going to minus 5. So when x goes to minus 5, x goes to minus 5. So this is minus 5. All right, so the upshot of this is, if you have some limit and the function that you're taking the limit of is just your variable, then what you get is just the place where you're taking the limit. Unfortunately, that's about all of the really easy examples of calculating limits, constants, and just the function x. For any other function, we're really going to need to know a little bit more about sort of how limits react when they have more complicated formulas inside of them. And to do that really precisely requires digging into the exact definition of a limit, which we haven't really done, and we will a little bit in the future, but I think the results that come from that are plausible enough that I'm not sure it's worth the time to prove these facts. So instead, I'm just going to list these facts. I'm a little hesitant to do this because I always feel like it's cheating to just throw out some facts and expect you to believe me, but these seem plausible enough that I hope that you will believe me. If your limit has the familiar operations inside of it, like you're adding things, subtracting things, multiplying things, or dividing things, it turns out that limits do exactly what you hope they would do. So if we have these two functions and the limits at some particular value of x, which I'm calling a here, if these individual limits exist, and when I say exist, that I mean that they have to be finite, then it turns out if you add the two functions, the limit of the sum of the two is just the sum of the limits. And it's the same thing with subtraction. So the limit of a difference is the limit of the difference of the limits. And it's the same with a product. The limit of a product is the product of the individual limits. If you have a constant, you can just pull that constant outside, which, this is number 4 here is just a special case of number 3. And if you have a limit of a quotient, it's just the quotient of the limits. Although we do have to be careful that the limit in the denominator shouldn't be 0. If the limit in the denominator is 0, then all bets are off. Also, there's one other situation, which is with exponents. As long as your exponent is constant, then the limit of a function to an exponent is just the same exponent applied to the limit. But this only makes sense when both sides are defined. Depending on the exponent and if the limit is negative, you might run into some domain issues. But as long as both sides are defined on an interval around a, then you can just pull the exponent outside the limit. Notice that this is true for any value of n. So in particular, it's true for fractional exponents, and that means it's true for roots, right? So another special case of this is that a limit as x goes to a of any root of a function is just the root of the limit. of the function. Okay, so all of these statements are essentially what you would guess about limits. So limits behave very nicely. So let's use all of these these all have names. I don't know if they're really worth naming. The number one is usually called the sum rule, the difference rule, the product rule, the constant multiple rule, the quotient rule, the exponent rule. So these are all what you would guess for limits. So let's use these to evaluate some more complicated limits. For example, let's find the limit as x goes to 3 of x squared minus 4x plus 2. Well, we can start out by using the sum and the difference rules to break up this limit at the subtraction and the addition here. So we get the limit as x goes to 3 of x squared minus the limit as x goes to 3 of 4x plus the limit as x goes to 3 of 2. Okay, so we've used the sum and the difference rules to get that. All right, well now for this first piece we have an exponent, and the exponent is a constant, so we can move that constant outside of our limit. That's the exponent rule. So the square of the limit as x goes to 3 of x. In this second piece we have a constant multiple, so we can just move that constant multiple outside. So 4 times the limit as x goes to 3 of x plus, and then for this last piece, well, this is one of the cases that we know, right? The limit of 2, it's just 2. Right? Remember, the limit of a constant is just the constant. All right. Well, now our remaining limits here, these are our other special case. The limit as x goes to 3 of x, that's just 3. So we get 3 squared minus 4 times, here's 3 again, plus 2. So 9 minus 12 is negative 3, plus 2 is minus 1. So this whole limit is minus 1. And we didn't have to resort to looking at a graph or making any approximations. We can be sure that this limit is exactly minus 1. All right. Oh, I guess notice that to use the limit laws here and here, we had to know that these individual limits existed. This limit and this limit must exist. But they do. I mean, we just proved that they do exist. We kind of did it backwards because we assumed that it would be okay, and then we found that, oh, it was okay, and that justifies our previous calculations, but that's okay. All right, for another example, let's look at the limit as x goes to 2 of x squared plus 1 over x minus 3. Well, as long as the limit of the denominator isn't 0, then it's safe to break this limit up at the quotient. So this is the limit as x goes to 2 of x squared plus 1 over the limit as x goes to 2 of x minus 3. So now in the numerator, this is the limit, we can use the sum rule, the limit as x goes to 2 of x squared plus the limit as x goes to 2 of 1. And then in the denominator, limit as x goes to 2 of x minus the limit as x goes to 2 of 3. Now limit as x goes to 2 of x squared, we can move that squaring outside the limit. So limit the square of the limit as x goes to 2 of x plus, well, here we have the limit of a constant, so that's just 1, over limit as x goes to 2 of x, that's just 2, and then limit of a constant, so minus 3. And then the only remaining limit is limit of x again, so that's going to be just 2. So that's squared plus 1, and then in our denominator, 2 minus 3 is minus 1. So 5 over minus 1, that's minus 5. So this limit is minus 5. You can see that in a lot of cases, we can just use the limit laws to pull apart this expression until it's easy enough to, or until we get to our basic limits where we're taking the limits of constants and we're taking the limits of just x. Let me show you one example that really demonstrates that these assumptions that we made in our limit laws, that these individual limits exist and that they're finite, really is necessary. So these limits have to be finite for this to work. As an example, let's find the limit as x goes to 0 of, so what I'm going to do is take the limit of 1 over x minus 1 over x. Actually, let me make it 1 over x squared. Now I know what you want to do. You want to say, well, look, this is just 0. And you're right, it is just 0, but we should be able to use the limit laws, except for the fact that the individual limits are infinity. But if we could use the limit laws, right, if it were okay to use the limit laws, then we should be able to say this is the limit as x goes to 0 of 1 over x squared minus the other one, limit as x goes to 0 of 1 over x squared. And right, this limit here, that's infinity, and this limit here, that's also infinity. So what's infinity minus infinity? Well, infinity minus infinity is undefined. That doesn't really mean anything. But over here, 1 over x squared minus 1 over x squared, that's 0. And the limit of 0 is 0. So if we let ourselves use the limit laws when the individual limits are infinity, we get nonsense. We should have gotten 0, but in fact we got nonsense. So that means that what we did here using these limit laws is not justified at all. You might say, well, isn't infinity minus infinity 0? But that's not right either. To show you why that's not right, let me do a slightly different example. Let's take the limit as x goes to 0 of 2 over x squared minus 1 over x squared. So if we could use the limit laws, this would be the limit as x goes to 0 of 2 over x squared minus the limit as x goes to 0 of 1 over x squared. And this limit here, that's infinity. This limit is also infinity. So is infinity minus infinity 0? Well, let's look at this side over here. 2 over x squared minus 1 over x squared is 1 over x squared. And the limit as x goes to 0 of 1 over x squared is actually infinity. So we should have gotten infinity, but we actually got 0. So that means two things. First of all, no, you can't use the limit laws like this if the individual limits are infinity, or if they don't exist. And the second thing it means is that infinity over infinity or infinity minus infinity is not 0, right? The reason that infinity over infinity isn't 0 is because we can't really tell how big these infinities are, right? These infinities aren't coming from nowhere. They're coming from this context. And it's true that each of these pieces go to infinity, but the first one goes to infinity faster, right? So it should sort of win. And that's why this limit comes out to be plus infinity. But as soon as you write down something like infinity minus infinity, you've forgotten where these infinities came from, and so you can't tell which one wins. And so that's why infinity minus infinity isn't defined.